Hi, everyone. So for today, um, usually what I would do is go over the lab solutions from yesterday for a little while and then do some new material on something called red-black trees, which are a way to make a binary search tree where it stays balanced because of the way that you write the code. So like when you do inserts and deletes and lookups and things like that, it always stays so that the depth of the tree is log of the size of the tree. Um, and unlike the trees that algorithms that we've been looking at in the dictionary code from the last few videos, you don't have to go through and rebalance at specific points like you would do have to for that. But since it's a little bit complicated and the red black tree stuff won't really come up in the rest of the course, I'll just post the notes on that and you can have a look at that if you want or not if you don't want to. And so we'll just do a quick video today to go over some of the lab solutions and talk about what you should take away from these examples. Okay, so if you tried the lab a little bit, you saw that we were working with the counter signature from last week, where a counter has a 0 and an increment and a show function that gives it as a string. And then there was this too much information TMI counter, um, where the idea is that if you implement counter by saying there's a type of counters, a 0 counter, an increment function, and a show function, and you just do it like this. You say the counter is int, the 0 is increment, the show. Well, that works because when you have a signature like counter, if it says there has to be a type of counters, a 0, an increment, and a show, and then in the implementation, you implement the type of counters as something, and then you give uh, a 0 that is of type counter, which is actually int, an increment function that goes from counter to counter, which is actually int to int, a show function that goes from int to string, counter to int to string, which is actually counter to string, then you're good. So the thing that's kind of wrong about this is that if you do TMI counter dot increment, then, for example, you can apply that to negative numbers and get a negative counter. And we might, have the idea that because the only counter functions are 0, increment, and show, like if these are the only functions you're supposed to be able to use, then it should be the case that all counters are always positive because you start at 0 and count up. So how did we break things? Well, we took a function from the module TMI counter dot increment, and we applied it to a random integer -2. And at this point, we're outside of the module, right? So we're like down here in some client code. And in the client code, we're not supposed to know that counter is really int. So if we want to treat this as a prescriptive signature and say that the only things you're supposed to do about counters are 0, increment, and show, then we shouldn't really be allowed to know that, hey, I can take any integer I want and feed that in, and that's a counter, right? We're sort of spoofing a counter in a way that we're not supposed to um, be able to do. And the reason is that if you say TMI counter colon counter and counter equals int, what happens is that the client actually learns the identities of all of the types in the module. So from the client's point of view, down here in the client code in the REPL in SML and J interactively, we know that the type counter is actually int. And the reason that SML does this is because there are times like what we're talking about in Monday's videos where you actually want this, because when you're doing a descriptive use of a signature, what you want is that when you like the ordered signature that we were talking about last on Monday, when you apply that to a module, you actually want to know that the um, counter is like the counter type is actually int because you're describing a bunch of functions that a type has without saying that that's all of the functions that you ever might run into. Okay, so then the question is, well, if that's the mechanism, if like clients learn the identities of the types in the signature, even though like this doesn't say that in the signature that the type counter is int, right? Because we did that implementation way back on uh, a week ago Monday, where we implemented counters as binary numbers, right? So we could do that, but we can do different implementations. But whatever the implementation is, the client learns of how the type is implemented. So how do we protect clients from that information? How do we keep the identity of the counters hidden or private or confidential? Well, the idea is that if we have what's called a private data type, like this, type counter equals hidden of int. So hidden could be called anything. Right, there's nothing special about the word hidden here. Like this could just be foo of int if you want. Um, then if we make up a data type inside of a module and we don't tell clients about that data type, then clients can't actually do anything with counters besides what's in the signature, because in order to do anything with the data type, the only things you can do with a data type are, one, you can pattern match, right? So you can write a pattern that breaks up the element, or two, you can construct values using the data type constructor. So if we want to write the increment function, let me do it a little more explicitly first, then we'll come back to that. Increment is supposed to take a counter and return a counter. So the way to get at the value inside of a counter is to say case C of, if it's hidden X goes to something. And in particular, if we want to increment the counter, then we want to return X plus 1, just like in the increment function here, we turned X into X plus 1. But here, the inside of the hidden constructor has type int, and then X plus 1 also has type int. Okay, so there's the slicker way to write this is we could just say exactly the same thing by saying that fun increment of hidden of X equals hidden of X plus 1. Okay, so what we're doing conceptually is hidden is a private name that nobody except the inside of the implementation of counter can see. And so down here, if I try to, oh, I'll have to finish the implementation before I try it down here. But down here, I can't say hidden of X, and so I can't open up a counter and I can't create one uh, in the client code. I can only do that in the implementation. Okay, so for the 0 counter, if we tried to say val 0 equals 0, then we would get a type error that the type and structure is an int and not a counter, and that's because we forgot to say, hey, I know the password for creating a counter, it's hidden. And so we can do that. And then finally, when we show a counter, we also have to open it up and then do what we were doing before. Okay, so that loads. So now, if I say int counter dot increment of -2, I get a type error because an int is not the same as a counter. On the other hand, if I say int counter dot increment of int counter dot 0, then I get, the counter representing 1. And if I say int counter dot please print that counter, then I get the string 1, which is what I want. So all the operations in the signature still work like they're supposed to, but now since I can't say, if I try to do case this of hidden int counter dot hidden of X goes to X or whatever, then hey, there is no hidden in path in counter dot hidden. That's because when you ascribe a signature like counter to a module like int counter, basically it restricts things so that the only things you can see are the things in the signature, which in this case are counter. There is a type counter, 0, increment, and show. You learn the identity of the type counter, that is what it's equal to, but you don't learn the value constructor hidden, and so you can't pattern match, you can't create values, and so the ability to create and uh, open up counters is restricted to the inside of the module int counter here. And so if there's ever a bug where you see a negative counter, you know exactly where to look. You know that like this code in int counter is the one that violates that invariant. Okay, so that's the idea of making a type abstract or unknown, or maintaining an invariant of the type that only the inside of the module has to care about, right? Nobody else needs to worry about negative counters because it's only the inside of the module that can create and destruct counters. So if you ever see a bad counter, you know that the inside of the module was responsible. So this is important because it lets you sort of pin down responsibility for problems, and that lets you decide where in your code to look when you notice that something has gone wrong. In this case, something going wrong would be seeing a negative counter, which shouldn't happen, but like in more sophisticated data structures, it would be like the thing that's going wrong is like your tree is not sorted or your tree is not balanced or something like that. You could know who's responsible for that by seeing that which module the type is defined in, and if stuff is kept private to that module, then you know that you're supposed to go look there. Okay, so that was the idea there. So a little bit on substructures and functors. So the next problem was to define an implementation of better counters. So for better counters, the idea is that a counter just provides an increment by 1, and a better counter is going to provide an increment by many numbers. And so we're going to write a better counter functor that takes a module, let's call it count, which is a counter, and produces a better counter. And so this is like a function that takes a module and returns a module. And the module that it returns is supposed to have a substructure named C, so structure C colon counter. And so inside of it, there's supposed to be a structure named C, and we define that to be the one that we're given. And so what we're doing here is we're seeing that inside of a package of code can be another package of code, right? So counter is a type of counters and a bunch of functions on them. And now we're making another package of code, which has type signature better counter, where it has all that stuff and more. And all that stuff is in a substructure named C. So to write the function increment many times, we get in C, which is a counter, and N, which is an int. And at this point, we have an unknown implementation of counters. So we can't say something like case C of C dot hidden X goes to blah, 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 right? So like we can't open things up here because we're writing this increment many times as if we're in the client code now, which means we can only do the stuff from the counter signature 0 increment show. We can't do other stuff. So what we have to do here is do this by recursion. So we can say if n is 0, then we've incremented c 0 times, and otherwise we want to do c dot increment of increment many times of c and n minus 1. Okay. And so now how do we use this? Well, better counter is a thing that takes a counter as input. So in order to use it, we have to say I don't know, structure BC equals better counter and feed it a counter as input. Well, we've got the int counter up there, so we can feed it that as input. And so then we can say something like better counter dot increment many times of int counter dot 0. And if we increment it 12 times, then we get that. And we can even say int counter dot show of that. Oops, and get 12. And so you might be wondering, like, why can we say show int counter dot show to a better counter dot increment many times when better counter increment many times returns the counter type coming from the C module inside the better counter module? And that's because we defined C to be count. And as input for count, we fed int counter when we applied the functor down here. And so SML propagates the fact that better counter BC dot C dot counter is the same type as BC as int counter dot counter. And that's because, well, we fed int counter as input to better counter. What better counter instantiates this C to is whatever we provide as input. So that's saying C is int counter. And so we propagate that. And so this is an example of why you want the functionality that was causing us trouble up above, which is that SML automatically propagates the identities of all of the type definitions. The reason you want that is that when you're building up bigger pieces of code by instantiating functors, you want to make sure that you remember what all the types are. And so the way we'll use the SML module system this semester is that we'll let SML always propagate things, and when we want to make a type private, define it to be a data type and don't export the constructors, then you can't pattern match and you can't construct values, so you can't spoof values of those types. Okay, right. So we can do that. We could also do, right, so we could also say structure TMIC equals better counter of TMI counter, and then we could do TMI counter dot show of increment TMIC increment many times of that. Okay, and then as expected, that doesn't work because int counter dot 0 is not the same as, right, is an int counter, right? And TMI counter is actually an int, whereas int counter is like a hidden int, and so that doesn't work. But if we get things consistent, then it works. So what's happening is that we're propagating the type information, but we're still keeping types that were different after the propagation. So that's how that works. And so if we wanted to, we also could have said tmic.c.show there. Okay. And we could have said tmic.c.0 there. So one thing to point out is that when you have structures inside of structures, the notation for accessing the inner things, right? A better counter has inside of it a counter. A counter has inside of it a show function and a 0. The notation is just to use repeated dots. So if TMIC has signature better counter, then TMIC.C has signature counter, and if something has signature counter, then it has a show value inside of it. Okay, so that's the main idea for the counter part of the lab.